make sure to mute everybody.
Yeah, let me make sure. Yeah, everyone is muted.
Except me?
Yes.
Okay. Okay, then I'll start. So welcome to the Lunch and Learn series without lunch, so it's only learn. Usually Doug does this introduction. I'm sure there is organizational remarks to be delivered, but Doug can't join us right now. Maybe he'll join us a little bit later. And certainly in the next Lunch and Learn series, we will learn about the organizational stuff. We decided we're going to record this this lecture anyway, just to have it also in the YouTube channel. And yeah, then maybe that's a good point to start and edit the YouTube feed right here. So, okay, so hello again. This Lunch and Learn lecture is going to be about resolution in microscopy, SIM, and especially SIM squared. Hold on, just 1 second. And especially SIM squared, in the form of a walkthrough. We will switch over to workstation number 4 and go through the settings on an exemplary set of SIM collected images. And the format is going to be discussed here. We're going to go through a very quick review and introduction to super resolution microscopy, going through definitions of resolution and super resolution. Then we're going to go to a quick walkthrough of the acquisition settings on the Lyra 7. Then the main part of the lecture is going to be SIM and SIM square processing, where we're going to switch over to workstation 4 and go through the different settings there are. And then we will take a look at troubleshooting and overprocessing, how to recognize the overprocessed images. At the end, I'm going to use this opportunity to sneak in some important content about channel alignment, which is an often forgotten yet important aspect of SIM and imaging on ELIRA 7, and finish off with a quick summary. So very, very briefly, resolution and super resolution is all about, well, in microscopy, typically spatial resolution. What we see here is the same object collected with different, with the same microscope with different processing parameters. On the left is what would be the conventional deconvolved or confocal type image. In the middle, we see the conventional structured illumination microscopy, and to the right, we see the enhanced details that are afforded by using the SIM squared procedure. And if we take a look at the finer detail, if we zoom in more and more, we will be able to see more and more detail. Resolution, of course, is the smallest distance between two objects so that they can be resolved. The typical limit is given by the physics of electromagnetic waves, and typically the formula for the smallest distance between two objects that can be resolved on a microscopy apparatus is the one carved in stone over here, it's the wavelength divided by the numerical aperture of the imaging system. For all practical matters, this is around 250 nanometers. This is what what we obtained by dividing 500 nanometer wavelength by 2, more or less. And that is the blurry boundary between resolution and super resolution. Anything that exceeds the 200 nanometer range, going down into 100-ish, and below nanometer range is called a super resolution technique. There is some overview of super resolution techniques that are available online or also here at HCBI. There is this booklet with the essential knowledge briefings from Wiley, where there is a very hand-waving sort of introduction to the super resolution methods, and there is a, let's say, more proper kind of overview paper by Shermele, Sauer, Eggeling, and other people in Nature Cell Biology, where it goes a little bit more in depth. Those are good starting points to review and recap super resolution if need be. Of course, we're not going to delve too much into that and going straight to the SIM and SIM2 processing. Before we go there, however, we go quickly through, what is structured illumination microscopy? How does it work on ELIRA 7? Very, very quickly, structured illumination microscopy works by overlaying a known grid or a known lattice, what we see here on the right side, onto an object of unknown shape. And what we detect there is an overlay image. And what we see there, and I don't know if this displays properly on your screens, is a series of beat frequencies, of lower frequencies, moire fringes in the images. That's typically what you see if you overlap, two pieces of cloth from a curtain, for example. You see these beat frequencies. This is what the physicists would call heterodyning, and the information of the high frequency information of the smaller object is ingrained or encoded in the low frequency, in the resulting frequency in this moire fringe, and that's something that can be detected and can be mathematically decomposed into and reassembled into an image with enhanced resolution. And in practice, it looks as follows. You would collect images seen here on top of microtubules or whatnot with that grid, and then this grid is reconstructed mathematically by looking at these beat frequencies, and the result we see on the lowest panel here, an excerpt from these microtubules. You see the microtubules better resolved on the left image, with in comparison to the right image, which is the wide field image of the same region. Okay, so now some time has elapsed, some like 10 years have elapsed since the first implementations of SIM and today. And one of the things that we all learned about SIM is that SIM is actually a two-step process. These two steps were usually done in a single process by taking the raw image and then reconstructing and deconvolving everything at the same time, as seen on the top line here. So you start with a SIM image, a SIM raw image, you reconstruct and deconvolve in one step, and you obtain the image on the right. And the one thing that was learned is, hey, since we are using this lattice pattern, we actually have a measurement of each dot of that pattern everywhere where it is. So can this information actually be used to further deconvolve the image using not a generic PSF or a generic point spread function for the system, but using a very specific one obtained from the image itself. So if we subdivide that process into two parts, that's how you get to the, let's say, SIM squared. That's why it's called SIM squared, is because you do SIM on top of the SIM image. and you obtain an image that is shown here on the lower panel. Let's take a look at the few differences between these two images here. And you see here on the left panel, typical SIM image is enhanced on purpose to show the background, and the background in a typical SIM image has this graininess, that shape that probably you all are familiar with. And that can be thresholded out, and there are settings that can be used to avoid this, usually at the cost of resolution. So, the filter settings cannot be too high, and you'd start to see this kind of background there in the back. In comparison, the SIM2 approach gets not entirely rid of, but is a lot less affected by this off-focus blur. So you can afford to use higher filter strengths and not be affected by that, by objects that are off plane. Okay, so before we go to workstation 4, I would like to show you here on the presentation, also because these slides are going to be saved on HCBI, where the SIM and the SIM2 adjustments can be found. So SIM processing can be done in an automated way or with adjustable settings. The automated way is shown here on the left side. I'm sure all of you know how to get to that part of the user interface. If not, it's shown here on the left side, where you go to processing. You have these methods, and you would invoke the SIM tab here, and that SIM tab would appear as shown here. So if using the automatic, the default, the autopilot, you see everything is set to default. The system will find the best settings to render the image. If we press this default drop-down menu here and select adjust, we see other options become available, and this is where we can interfere with the system and use different filters and different parameters, and we will take a look at that in a moment on workstation 4. The SIM2 functionality is that button that is shown over here on the left. Once that is ticked on, that takes us to the SIM2 menu that we will see in a moment. There is an additional document that I'm going to put there at the HCBI collection of documents. That is this user guide for SIM2 processing that was done by the engineers at SAIS to guide a bit the settings that can be used and how they are used and how they generate the images, and what parameters can be used if we veer out of the automated settings and go to adjustable settings, how to use them and how to judge the images. Okay, so without further ado, I'm going to share the next screen. We're going to be taken to, here we are. We're going to be, hopefully you see this. Kwesi, can you quickly confirm if you're seeing workstation 4?
Yes.
Okay, so here we are at workstation 4. I have loaded an exemplary image here. That's some human brain cell. I have no idea what the staining is. I know it is some kind of perinuclear molecule stained here with 3 colors: green, red, and far red. And I'm going to take us to the SIM menu here on the left side. Should I increase the font size here? Do you feel like it's better if I zoom in?
Yes, that'll be good.
Okay. So first of all, I'm going to reconstruct this image here without the SIM2. This is just an excerpt of a larger image to keep our computation time manageable. First of all, I'm going to not use the SIM2. I'm going to generate an image using regular SIM with a standard sharpness setting. So if we apply that, the machine is going to reconstruct the SIM image, and there is a little bit of misalignment that you can see here, and that's why I was alluding to the channel alignment part that we will do in the final part of this lecture here. But let's not focus on the misalignment. Let's focus perhaps on the image as seen as one channel. In the green channel, if it's even difficult to increase the noise levels here, but it's a pretty good image. If you take a look at it, we can see here details of that perinuclear region here. If we care to measure how large these objects are, we're getting somewhere in the vicinity of 160, 120 or so nanometers per image. If we choose a stronger filter, we will start to see, let me choose here on purpose a stronger filter, we will start to see background affecting the image more and more. Yeah, it starts to become a real problem to look at this green channel without the background here starting to creep up everywhere. So we all know and dislike these sort of overcooking artifacts over here. Okay, so when we turn to SIM2, all we have to do is click on that SIM2 box, and then the difference is shown here. Is if we have the sharpness filter here is weak, standard, strong, wide field, or deconvolution. When we go to SIM2, we have choices here again. The choices are a little bit more fanned out. We have situations where we have live cell, where we have fixed cell, and we have low contrast. There is weak, standard, and strong, and low contrast images. The guideline to choose between live and fixed is almost there is very little difference, if any, between the live settings and the fixed settings, but the bigger difference is between weak, standard, and strong settings, and how to choose that is to go to the original image and look at the histogram, and what we want to figure out is the contrast between signal and the noise and the background of a particular image. So if we go, for example, to this green channel here, and we take a look at the background values, there are around we can see this value here at around 500. And if we look at the signal values, which would be somewhere on the upper part here of the histogram, we have values at around 3000 grayscale values. So there's a factor 6 between the darker areas and the brighter areas here, more or less a factor 6. A factor 2 would be somewhere over here. We clearly see, that the parts of the image that are interesting are clearly brighter than a factor 2 to approximately a factor 6. And the guideline in that guide is whenever you are in an area between 2 and 5, then the setting here will be weak. Whenever you are in an area between 5 and 12, you would be using standard strength. If you are above 12, you can use strong settings, so then the signal to noise ratio is sufficiently high to go with a stronger filter. If your signal to noise ratio is even stronger than 12, say it's at around 15, 18, 20, then there is a way, and we will see that a little bit later, to override even that and to go even stronger settings, where on very bright samples, 60 nanometer resolution have been achieved using these settings. Okay, so let's and I would invite anyone that is interested with a SIM2. I'm sure lots of you have used that before, to come to Workstation 4 with your data, also with previously acquired data, and try the SIM2 settings out. So SIM2 activated over here. We have here a factor 6. So here it was suggested to use strong settings. Or no, actually, sorry. Standard settings was somewhere between 2 and 5 would be weak. Anything above 5 would be standard. So we can use the standard settings over here, and we can hit apply, and that will then calculate that image for us. Then I would like to put them side by side. The regular SIM image and here the SIM2 image, and we try to look at the same area here. Not sure where this area is, but I think we can go and zoom in there. That's somewhere over here. I think it's this little blob here. Gets resolved slightly better than it was before. I think, yeah, I think that this here is the better comparison between these two areas. So now we can go and we can see this sort of difference here. That was right, this edge of this object here. Oops. Going back in there, that was this little edge over here is that edge over there, and there we're getting to some sub 100 nanometer resolution of this object here. We're not going to achieve, with that signal to noise ratio, we're not going to achieve 60 nanometer resolution, but we're going well into an area of, below 100 nanometers, some 90, maybe 80 nanometer can be resolved with that kind of image quality here. So what happens if we okay, maybe I should rephrase this. For regular usage, it would be sufficient to just go and become guided by this, selection of the background to signal and use weak, standard, or strong settings. But what happens if we go and we override these settings? Let's take a look. Let's try to push that envelope, and we would go to adjustable settings over here, and we see here we're not going to use standard, but we're going to use strong. We see two main sliders here. One is called iterations, and the other one is called regularization weight. The regularization weight is similar to the filter that was previously used, in that the smaller this number is, the smaller the features also become, or the more intensive the filter is going to be. And iterations is the number of repetitions that this filter is going to be used on the image. Now let's go crazy and push this to like super high values to see how artifacts look like. And here we will need to oversample the output as well. The computation is performed on the GPU. We have increased here the number of iterations quite a lot, so that's why it's taking so long. I hope it will give us a very not nice image with loads of artifacts, because I was really trying to push the envelope to something that is unreasonable. And yes, it is very unreasonable. And we see here, as we increase the background, everything becomes very punctate. Everything coalesces down to little dots that are very unintensive. And as I go to the different layers, yeah, they completely vanish. So this object here, for example, only exists in plane number 44. As I go up to plane 45, this is gone, or to plane 43. This means that the algorithm somehow collected all the intensities that were above and below this layer and coalesced them all into this little dot here. So one telltale sign that something is awkward or wrong with your reconstruction is when you see objects available only in one plane and then vanishing in the next one. Yeah, I don't see too much background artifacts here. Everything became very punctate, but not the typical squiggly worms, which is something that I would have preferred to see, because it's so much more telling that the settings were overcooked. But where everything becomes single dots is also an indication that the settings are overcooked. Maybe in the other channels we will see it better. Was there more background here? No, everything punctate as well. Over here, yeah, everything got corroded to the point where everything is just one single dot. I think it's so severely overcooked that, oh wait, yeah, objects only exist in one plane, which is very unreasonable. We can try different settings. I don't know, maybe remove the filters here. That should also cause a very artificial overcooked image. I guess it's one of those things where you will immediately see when there's something wrong with the image, if objects appear only on one plane, or if the background is unreasonably high. Again, it was very easy to see it on the regular sim image here. as this background becomes with this worm-like kind of structure. It's a little bit harder to detect here on the SIM2. Okay, is it done yet? Okay. All right, what happens if we increase? Oops. Take a look at the single channel. Yeah, there we go. We start to see worm-like structures here as well. Oh, these are all the area rings. Oh, in this case, it's not so much the worm-like structures, but the appearance and disappearance of objects as they move to different planes. Everything looks like it's single dots that exist only in one plane. Maybe larger objects become more worm-like. Yeah, very unreasonable objects. So when going to milder conditions of imaging, such as we had before, like over here, the structures do not vanish from one plane to the next. You see here, it's not an artificially reconstructed dot that where all the photons were sent to one plane and everything else was corroded and eroded. That's what would be expected from images that are not overcooked. Okay, so to recap, the two main tools to play around with, if you feel like doing that, would be iterations and regularization weight. I prefer to stick to the weak, standard, and strong settings. Going with the default settings, they do a pretty good job. It's only when you're trying to push it to higher limits by using technical samples, DNA constructs, and things of that nature, with fixed base pair distance, then adjustable settings would make sense. Otherwise, the presets are covering all bases. Channel alignment is another issue that I don't know if all of you pay too much attention to that. I've seen a few instances where channel alignment is not that necessary. If you're looking at a single channel, it's not required to do a channel alignment. You would align the channel with itself. Doesn't make much sense, but especially when doing object colocalization and trying to look at the coincidence and the colocalization of two objects, it becomes very important, especially in super resolution, to have some form of channel alignment. Let me show you what channel misalignment looks like. Maybe we can take a look at this very same image here. As we zoom out, let me remove these graphics here. And we can see here that even these bright structures that are here on the side, that they don't align quite well, and that these structures here are also always consistently to the left and to the right, and always the far right channel is always to the right of the green channel. And you would expect, if it was like that, you know, vesicles like these would appear not always with the channel on the right of the green channel, but you would expect this to be randomized a little bit out. So it's clearly an issue of the channel alignment in this case. And the way out of this is to, well, in the case where you have a system where the channels are clearly visible like that, you can try to do the channel alignment on the image itself if you have objects that contain all the three colors. And I'm going to run this very, very quickly through that. And this is done by invoking the channel alignment and by selecting the image that needs to be aligned. And here the fitting checkbox has to be turned on. And on an image like that, you can hit the apply button and the final result will be an aligned image. So if we go back to this is the aligned image and compare it back to the where is the non-aligned image? Is it this one? Yeah, there it is. And we take a look at this area here, and we take a look at the very same area over here. We see now that the alignment has taken place. Now also this object here versus this object here, you see clearly misaligned, and here you see clearly aligned. And yeah, so in case you have a structure or a cell or a specimen where you have obvious structures on the side, pieces of dirt and whatnot that must align, then they can be used as almost as fiduciary markers to align the rest of the image. In case you don't have such structures, the only thing that can be done is to resort back to alignment, to alignment using a bead sample that is by the system. Here is an example of a Z-stack collected over the 4 channels of beads. And here again, the procedure would be to go to these beads, do the SIM processing on these images. Okay, I think I lost the connection or it's taking too long to update. Yeah, here it is now. Getting this, we don't have to do SIM squared necessarily, but we could do a weak SIM squared image processing on these beads. This will generate now an image. Since these beads contain all 4 colors, these beads must be co-localizing. And we should see here in the resulting image that they are not naturally co-localized. And by applying the channel alignment, we will retrieve a table. Just a little longer. I've cropped down these images to reduce the calculation time a little bit. Whenever you're trying to look at features of your sample, that might be a good idea to crop them down first and appreciate only a smaller area of it. That way you don't always have to recalculate the entire image. Okay, so that's the natural misalignment of these beads. If we take a look, and this is especially in the Z direction, if we would take out, let's say, one particular bead here, this one, and we take a look at it in XYZ, and we take a look at where that's where the blue is, that's where the red is. Okay, so we have to go back to min-max this out. The green. Yeah, here you see directly that the alignment is, yeah, there is some misalignment between the two objects, especially here in the Z direction. Okay, put this back to the minimum maximum, and if we remove this graphic here and zoom out again, and we apply the channel alignment, again, the process is you'd select the image you want to align, you want to generate a fit. There are two options, either a lateral or an affine transformation. Let's do the affine one for here. The affine transformation includes some rotation and stretching, and we apply that procedure to those beads. Okay, that resulted in a better aligned version of what we saw before. So if I go and collect the same bead that we had before, it was, I think it was this one here, and check the alignment of it between the red and the green channels. They are exactly on top of each other. And that was not the case with, no, it's starting to get too many images over here. Yeah, that was not the case over here. Right, so that's channel alignment. Please don't forget to do your channel alignment. It's also a good opportunity to check out, if the imaging system is performing okay. The beads should be nice and round and not banana shaped or have any weird kind of features dangling out of them. So I'll go back to the presentation to, okay, where were we here? Kwesi, can you confirm we're back in the presentation?
Yes, we are.
Okay, so over processing, we just took a look quickly at the over processing. We did not look at elongated structures like microtubules. This is an example. I couldn't find a good example to showcase here, but what would be seen on an overcooked image with elongated structure would be, you would have like single pixel kind of structures. Again, same thing that we saw when we move, one layer up and one layer down. Everything seems to coalesce onto a single layer or onto a single pixel. Especially at bifurcations, you would see structures like these that look very unreasonable and that look like they consist of a single pixel. The other telltale sign is when going into the background, you would have worms instead of individualized dots. And how to counter that is to use less iterations or a larger number for weight, or a less, instead of 0.0001, you would use a couple of decimals less, and or to choose instead of strong settings, you'd go to standard settings. Instead of standard settings, you would go to weak settings. There's an additional setting if the signal is really low. Whereas if we could find here, if we go back to that screen, if we go to raw image like this one here, and we go to SIM settings, where is this SIM here, and here in SIM squared, there is an additional setting down here that's called low contrast. This would be typically used for larger objects where the enhanced resolution does not play such a big role. An example for this would be a cell nucleus, or objects that have very low contrast, that have very low intensity. The images in the end will not have the sharpness of the super resolution image, but they will be reconstructed together with the image. It is possible to select individual channels with different settings. For example, if your green channel has the possibility to use strong settings, and your red channel would have a different setting, and you could use different settings for different channels, or use a common setting for all channels. It is possible to assign different settings to different channels and calculate them at different strengths. So we go back to the presentation screen here. Okay, so we're coming to the end, and yeah, so we saw a quick review and intro into super resolution microscopy, a very quick overview of SIM acquisition in ELIRA. We focused a bit on SIM and SIM squared processing. Maybe another word of encouragement to try out different SIM squared processing settings. Ask me or Kwesi or Doug all the questions all the time. The workstations are there to be used. Since it's only quote unquote processing, nothing bad will be happening to your sample as you try different settings. We took a look at some telltale signs for overprocessing. The channel alignment, we gave it a very quick recap. I have included this in the slides here, just in case you want to reference back to what is happening on the slides. That's the difference here between no alignment, a lateral alignment, and an affine alignment, especially in the peripheral regions here. You see, if you have an affine transformation, it stretches the image also to compensate for residual chromatic aberration. These slides are included for further reference, and the channel alignment can be included into the SIM settings by checking the channel alignment checkbox and providing the channel alignment file or pointing to the channel alignment file there. Then the output, the resulting images are aligned already, so no further channel alignment will be necessary. Okay. The take-home messages is SIM squared as an evolved SIM processing algorithm greatly reduces background and improves resolution, is available on workstation 4. SIM square strength depends on raw image quality. Here the guidelines again. You would use strong if your signal is better than 12. You would use standard settings somewhere between 5 and 12, weak from 2 to 5, and poor contrast or even lower filters if you have a signal to noise ratio or a max to min ratio that is smaller than 2. Number 3 take-home message is don't forget to verify your channel alignment, especially if you're looking for object co-localization. Then with that, I would like to, we can stop the recording, and I would just say thank you, and we have a little bit of time for questions if there are any.